Right, good afternoon, everyone. How's everyone doing on this, I guess, the end of the blizzard now? Should be lots of snow. For the very first time in my life, had to shovel a car out of the snow this morning. We don't really get this much snow back in the UK. So I had to shovel my wife's car out on the way to work this morning. And I can see why they warn old people about getting heart attacks from that. Because I like to think I'm pretty fit and healthy, but bloody hell, I was out of breath doing that. So not here to talk about that today. We're here to go on with more of this laboratory course. So how did everybody get along with lab 1, or the video thereof at least? I do apologize for the audio in that. That has annoyed me no end. There's a good lesson in filtering there as well. Because of the way that I was recording those two mics, there's no way of separating those two streams from each other now. And that's really annoying. Like, I've now made that mistake, won't make it again. As long as you guys can understand, that's fine. And in future, I'll make sure things aren't recorded like that. So I'm also working from my at-home setup at the moment. I'm not in work at the moment. So things aren't quite as good, but maybe apparently the frame rate's good. So maybe my internet is better than IIT's. That's good. So we're going to go over a couple of things today. We're going to look at voltage dividers. So we're looking at voltage dividers because they're really useful. We use them a lot in analog electronics to get a voltage that we actually want, and we want to be able to understand them and understand how they work. So we're going to look at voltage dividers, and I'm going to construct one in a laboratory in a few weeks' time. I'd like to spend lab 2 this week as a virtual lab, and in that we're going to try and understand how ADCs work. So who has used an ADC before or knows what it stands for? So Mario has. Mario, what does ADC mean, and when did you use one? It is an analog to digital converter, that's right.
Professor?
Yeah.
I just had a quick question. So for lab 1, it's watch the video, create the graphs, and then do the test that you put up, correct?
Precisely that.
Okay, just making sure.
Okay, cool. If you've got a question that's not particularly pertinent to the very thread that I'm on, if you wouldn't mind leaving that to maybe put it on Slack, that would be superb. Okay,
yeah.
Cool. Right, so analog to digital converters, we're looking at those today. We're going to understand how they work. You guys are pretty fortunate, I think, in taking this lab course online, not doing it in person. You've heard my thoughts on you guys don't want to be technicians, but we get to do a virtual exercise with ADCs that you wouldn't do otherwise. And this will teach you how they work, that's useful, and probably puts you in better stead than the rest of your colleagues. So we're going to get that second. We're going to hit these voltage dividers first because those are useful. So has anybody here heard of a voltage divider before? Other than in the preceding slide. So Mario has. Mario, can you tell me where you used a voltage divider? I will not wait too long. I'll just answer this anyway. Okay, so we're going to look at voltage dividers. Now, voltage dividers are incredibly useful because they allow us to take a voltage. There we go. Alexander says stepping down voltages. They allow us to step down AC and DC voltages. Now that's incredibly useful. So we will, in general, draw a circuit that looks something like this. So we have some DC, I've drawn this as a DC circuit. We've got a DC voltage source, and we've got two resistors of known resistances here. So we can use, and these are really useful because what this enables us to do is to measure the voltage or the potential difference between three different points. So we would say the potential difference across the first resistor would be V1, and the potential difference across the second resistor would be V2. So this is going to be really useful for us. So we've got our input voltage, and there's two possible output voltages we can get here. It's difficult to think of, you might not necessarily think of these as being outputs, because when we construct a circuit like this, we're not necessarily certain what we're doing with it. But I'll tell you that in some of these laboratories, we end up using voltage dividers to take a really big voltage and turn it down into something more manageable. So the voltages that we get out are a function of the inputs and these two resistances here. So we're going to work out how we can determine them. So there is a current in general in the circuit. So we'll call this I total. Okay, I total is the total current, and we can see the way that I've drawn this is it's flowing from the cathode to the anode. Okay, that is the definition of the way that current flows. Does that strike anyone as slightly weird? Anyone got a problem with that? Because you should do. Sean, why have you got a problem with that? Bingo. So current is defined as flow from positive to negative. That is the definition of positive current. Okay, charge carriers, they're normally electrons in the sort of circuits that we're going to make those flow in the opposite direction. So we can just sort of ignore this little bit here, but we'll define and we'll remember the definition of current is flowing from positive to negative, okay? So it's actually it's the empty space where no electron is. That's where we define the flow of current, okay? We don't need to think about it too much, but I want to mention it because it might keep you awake at night after this lecture. Otherwise you'll think, Professor Smith said current was positive to negative, but electrons go the other way. So I've saved you from a restless night. See, I'm so in touch with how you guys think. So we've got this total current here. How can we determine that current? I'll just accept the name of the law that we can use. Ohm's law, David. Good, good. Okay, so we can use Ohm's law to get the total current. So let's put some values in. Let's say that my V in is 10 volts, because I can use 10 easily in mathematics. Let's say R1 is 100 ohms. And let's say R2 is 120 kilo ohms. So how can I determine the total current? V equals IR, that's good, that is Ohm's law. What is the R in that expression? So determine the total currents. We need the total resistance, Caitlin, that's good. And Carla said R1 plus R2, Timothy said R1 plus R2. So some of you are hot on this, but we're going to take a slow start with this lecture and we'll get there, okay? So determine the total current, we need the total resistance. So R total is equal to R1 plus R2. And for us, that's going to be my numeracy is actually really bad. So you need to double check when I add numbers up. My wife teases me for it all the time. I can't add up like my scores when we're playing cards. I can do line integrals, but I can't add up this stuff. So just double check my numbers for me, okay? Maths is easy when there aren't numbers in it. So this is the total resistance now, which means we can determine the total current using, as someone correctly said, V divided by R. So the total current is I is equal to V divided by R. So that's going to be 10 divided by 120,000 and 100. And I can't do that in my head. So my total current's a really small number. Okay, so 83.26 microamps would be the total current. And that's because we've got a really big resistance. I chose some silly large numbers here. Okay, so what that means is that the current everywhere in the circuit is going to be exactly the same. Okay, so that's one of Kirchhoff, I think it's Kirchhoff's current law. So we know that's going to be the current everywhere in the circuit, which means that if we were to look at these two resistors in isolation, they would have the same current going through them. Which means we can immediately use V is equal to IR to determine these two voltages here. Okay, because we've got V, sorry, we haven't got V, we've got I and we've got R, so we can determine them. So V1 is equal to I total multiplied by R1. So it's going to be 83.26 multiplied by 100. So I'm not going to bother with multiplying that out correctly. And then V2 okay, I'm not even going to bother multiplying these numbers out because that's just the numbers that we're going to get. So whenever we've got a voltage divider like this, we don't have to go through and work out the current every time. We can just use the handy expression and we can prove it quite simply. If we hadn't put numbers in above, well, in fact, let's just do it now. Let's say that's, say I don't want to have to work out the current each time. Up here, I could say, well, this is my I total. I total is equal to V in divided by R total. So for a voltage divider where I've got two series resistors, that's going to be V in divided by R1 plus R2. Okay. And then these expressions here, these it should be fairly easy to see that V1 is simply equal to V in multiplied by R1 on R1 plus R2, and V2 is equal to V in on R2 over R1 plus R2. Let's move that outside of my ugly mug. There we go. Okay. Simple. That's the expressions for a voltage divider determined. So who, again, I'm not trying to put anyone ahead or behind in this class. I just want to see where we're at. I like to know whether I'm teaching you new things or not. Who's seen this before? We've all seen it before. It's nice to have a refresher sometimes, isn't it? See things from a different perspective. Also, it makes for an easy class sometimes, I guess, but things are going to get more difficult. Okay. So this is how a voltage divider works. Okay, those are the expressions that we've got for a voltage divider. Now, the thing that's really useful for us, and the reason why we can use these to step down, well, we use these to step down voltages, We can use them to step down voltages because these numbers are always going to be less than 1. Okay, that's going to be less than 1. That fraction is going to be less than 1. So we use them to step down voltages. Now we can use them to step down both DC and AC circuits because resistors don't care at all about the frequency of whatever current or whatever current is through them or whatever voltage is being applied across them. Just a point to note there, even though I said resistors don't care, that's not particularly good English, okay? We should say resistors are steady state analog electronics. If you talk about inanimate objects having feelings, that's called the pathetic fallacy, and don't include that in any science writing or I'll put a big red line through it, okay? So we say resistors are steady state analog electronic devices, meaning that their properties in general are not a function of time. Can anybody think of an analog electronics component that does care about the frequency of the electrical signal applied to it? I'll be impressed if you can get it. Begins with a C. CPU wouldn't necessarily be an analog electronic component. That would be a real complicated digital thing. Capacitor. Cool. Okay, capacitor. Capacitor cares. Or capacitor is not a steady state component, I should say. And we're going to talk about that. So we now know how voltage dividers work. What I've written down here is that capacitors are slightly different in that it matters what we apply against, or sorry, what the frequencies we apply against them. So we're going to build a series of circuits that contain both resistors and capacitors. These are called RC circuits, okay? So we're going to build those and we're going to analyze them because these are really good circuits to help us understand how transient phenomena occur. So transient phenomena just means something that's varying with time. So we'll say that often as engineers, we wish to explore transient phenomena. So as engineers, we wish to explore transient phenomena. Now, the procedure that took place in laboratory 1, let's have a think about what actually occurred. So I had a circuit on the breadboard. I was speaking with a really annoying echo, but what we saw occurring was sampling the circuit using some probes, taking a physical quantity in the real world, which was the voltage, and turning it into a number in volts. Doing the same thing with the current, taking the flow of charge, which is just a physical quantity in the world, a property of the universe, turning it into a number, which is a human meaning, and then writing that down on a page. Now, it might seem like a simple thing that was done, but it's actually quite a complicated bit of work that took place. And I'm not trying to big myself up here. I don't think I do a particularly good job. But the complicated thing that's happened is there's this sampling of data. So I've chosen an instant in time to look at what's going on in this circuit, selected that value and turned it into a number that means something to human beings. So we've taken data, we've acquired data. Okay, now we obviously can't always do that. The process of writing numbers down, mainly because your hand would cramp up, it would get tiring. But secondly, we can't do it fast enough for a lot of the things that we want to look at. And thirdly, it's imprecise to use a human to do things. We're lazy, sloppy sacks of meat that aren't particularly good at doing a lot of things. And we cost a lot more to pay someone to do something inefficiently than it would be to get a computer to do it really well. So we're going to look at the process that takes place when we use an analog to digital converter to do that job for us. Because fundamentally, that was the job that I did in laboratory 1, taking quantities that exist as physical quantities in the world, turning them to data, and that's the process of analog to digital conversion. Might sound like I'm overhammering the point there, but I want to remind you all that actually the procedure of doing that is really complicated. Your body is capable of doing a tremendous number of things that computers actually can't do very well. For instance, I teach this to my flight mechanics class. Your inner ear has something called the vestibular apparatus in them. And so the cilia that detects your orientation in 3D space can only detect angular rates. So if you know your spatial orientation, that means something in your head is doing integration. Even if you are shit at calculus yourself, your head can obviously do it, okay? So that's the reason I try and point these things out, because these processes that we use and understand as human beings, we've got to try and write down processes for as computers. So we'll say the process of taking physical quantities at successive instances in time is called data acquisition. So what we're doing there, taking the physical quantity, this could be force. Okay, force is just a quantity in the universe, number of newtons. It's kilograms per meter per second, sorry, kilogram meter per second squared. Okay, nothing about that actually has a numerical value associated with it. It's just a physical quantity in the universe. We turn it into a number in newtons that we can write down on a page. We've done two things here. So we've picked a moment in time at which to select that value, and we've turned it into a number. Okay, because I'm sort of freewheeling this lecture. Some of my sentences aren't particularly great, but we're saying in doing this process of taking a physical quantity and turning it into numbers, those physical quantities in the universe exist in the analog world. They are infinitely resolvable, both in value and in time. And what we've done to turn it into a number, we've had to choose how many decimal places we're going to write it down to. So that's set the value. And then in terms of how quickly we can write values down in time, that sets our sample rate. So we'll say the precision sets the smallest meaningful change we can register. And again, we can think about that as being the number of decimal place. And then the sample rate simply sets the number of values that we record per unit time. So our choice of how we acquire the data, so how we're using an ADC to do this job for us, is going to determine whether we've got the correct choice for both the precision and the sample rate in here. So we're going to look at how an ADC actually does that. So we're going to look at these two things separately, time resolution and then value resolution. Okay, time resolution sets effectively what our sample rate is. And then value resolution, there's lots of things that can go into this. And this then comes down to something, we're going to look at something called bit count. And then we're going to look at ADC range. And then I'll put in brackets here, amplification, because we might need to think about amplifying some of these signals. So let's have a look first at this time resolution, how we choose that. Let's say I've got a continuous signal that exists in the real world, and I'm going to put my analog signal on here in blue. It's a function of time, and I haven't got any units for what its value is. I don't really care. So this here is my continuous signal, some sort of harmonic signal. Okay, so this is in the real world, and because this is in the real world, if I zoomed in here and made this really big, I'd get a smooth curve, no matter how many times I zoomed in, notwithstanding my crappy drawing, we'd always get a smooth curve because it would be a continuous function. Okay, that's what we mean by having a continuous function in the real world. So let's say, for example, that my signal here, that's 1 second. Okay, if this was 1 second in here, approximately what would the frequency of this signal be? One. What's the units, Mr. Jackson? Hertz. Hertz has got a capital H, by the way, but you're right. Okay, so this would be a 1 Hertz signal. Okay, so let's say, for example, I'm going to sample this signal using my analog to digital converter. Now, my analog to digital converter has no idea what this signal looks like. All it can do is it can take samples. So it can take a sample multiple times of whatever the signal value happens to be. And so on. And it's going to take those at fixed intervals. So the distance between each of these, that's going to be 1 over fsamp. And fsamp is the sampling frequency. So that's going to be the time interval that occurs in between each one of those samples being taken. So let's have a think about this. Now, if I want to reproduce this signal, then if I were to join up each of these with a straight line, then I'd get a pretty good reproduction of the blue signal with that many samples being taken. I could take many more, I could take loads of samples, but I just have a bunch of redundant data there. And if I've got to take all that data, I've got to record it somewhere. And I'm probably going to record for an interval longer than 1 second. So I don't want to take too many samples. So in the interest of avoiding oversampling, we want to work out what's the lowest number of samples I can get away with and still determine the frequency content of this signal. So we're going to think about this. So we don't want to take too many samples. Because that is oversampling. And oversampling isn't necessarily a bad thing per se, but it's just too much data to record. So we don't want to take too many samples. So what's the minimum number we can get away with? I'm going to ask you to answer this in a second, Mr. Bourne. That sounds good. So let's say that I've got my original signal here. Okay, Timothy said for a wave, probably 4 per wavelength. That's what you said there. So this is my original continuous signal. So Mr. Bourne, would I be right in saying you're choosing one here, one here, one here, and one here? Is that what you're saying in the chat? Okay, good. And this is actually the pitfall that I wanted you to fall into. So don't feel bad when I tell you this is wrong. So if I joined these up, can you see what's wrong? So it's too many for this point, okay? So in fact, you wouldn't need to take that one. You wouldn't need to take that one. And you wouldn't need to take that one. Okay, it's good because everyone always falls into this pitfall and that's fine. And I'm expecting you to make that mistake. So we've actually seen that the minimum number, if I want to work out what the frequency is of this signal, is just 2. Okay, because that enables me to capture the peak and the trough of this signal. If we take 2 samples per wavelength, so if we capture 2 samples per wavelength, we capture the frequency information. And I'm going to elaborate on what this means in a second. But before we elaborate, we're going to give this a name. Does anyone know what the name of this theorem is called? It begins with an N. An NY. This is good because this shows me that I'm teaching you new stuff, which is good. Okay, so this many confused faces shows me I'm teaching you new stuff. This wordy explanation here, we could say, we'll say f samp must be greater than or equal to twice whatever your signal frequency is. Greater than or equal to twice the signal frequency, and that will ensure that you capture 2 samples per wavelength. This is called the Nyquist theorem. Sometimes called the Nyquist-Shannon sampling theorem, but I've only ever known it as the Nyquist theorem. And this then means that FNQ, which is the Nyquist frequency, is twice whatever your signal frequency is. Okay, so if you know, for example, that you have a 100 Hertz signal, if you want to be able to reproduce that signal correctly, what is the minimum sampling frequency you need to sample your 100 Hertz signal at? 200 samples per second is what you need, Aaron. So 200 Hertz would be what you're taking it at. Okay, so that's all well and good in this sort of contrived example that I've got here, where I've drawn my continuous signal starting at 0 very handily. Okay, very handy the way that I've drawn that. So let's put a new slide. So we'll say in the contrived example, we knew exactly where that continuous signal started, so that was useful. FNQ is twice the signal frequency, so that's this one here. Is that what you wanted? Cool. But like, what is it? Does anyone think they could answer that question? Mr. Jackson's put in the chat. You put the Nyquist frequency, that's good. So this is the Nyquist frequency, good. And when I ask that, it's not because I'm trying to put someone on the spot, it's because I want to see if I haven't explained it. So if someone can answer it, then that's good. Okay, so in the contrived example, we set the continuous signal to start at t is equal to 0. And that's really contrived because that presupposes that we know exactly how that continuous signal works. So let's imagine another situation. Okay, I'm always bad at drawing this. So the way that I'm going to draw it is, let's say we've got our continuous signal. It's a terrible sine wave that I've just drawn. But let's say that we're going to start our time here. And so my samples, I'm going to take my first sample at time 0. I'll then take my second sample half a period later. This would be sampling at exactly the Nyquist frequency. Okay, this is more like what we'd get if we sampled at the exact Nyquist frequency. So if I was to reproduce this signal, we'd see something here. We'd see that the period of the red signal, which is the reproduced signal, would be correct. We'd get the correct signal frequency if we sample at the Nyquist rate. But what don't we get? What's different between the red signal and the amplitude. Good shot, Mr. Bourne, and also Thomas on there. So unless we're very, very lucky and we're sampling at exactly the Nyquist rate and we happen to get the peak and the trough, we'll get a different amplitude. So unless we are uncharacteristically lucky, we'll probably get a reduction in amplitude. And there's a name for this. Okay, the name for this reduction in amplitude is called attenuation. Okay, so we get a reduction in amplitude if we sample at exactly the Nyquist frequency. What we probably will more likely see, and I tend to be really bad at drawing this next bit because I'm not a computer, which is going to be the purpose of laboratory 2. What we're looking at in this lab is we're going to simulate this using Python, and you're going to change the sample rate, change the signal, and you're going to see all of these things build up in real life. And actually, it's pretty cool. I like this lab. It's one of the ones that I wrote rather than the ones that I inherited. So obviously I like it. But let's just have a think about what happens if we sample at not quite the Nyquist rates. So this is my signal. This is my time. God, that was terrible. Let's try that again. I'm going to do a few of these. Okay, so pretend I've got a signal that's a perfect sine wave. If we're sampling, say, just slightly higher than the Nyquist rate, let's say my first sample is taken perfectly at the peak. This next one is going to be slightly ahead of the trough. This one's going to be slightly behind the peak, slightly even further behind the trough, and so on. And then it's going to, I've got to think hard about how this works. So then what we'd see here whilst we'd still get the frequency correct, we would see the amplitude reducing and increasing with time. And this will happen much more often than this up here. Okay, because we don't necessarily know the exact frequency we're trying to measure. We should just know broadly where it is. Okay, so we'll see this sort of thing occurring more often. Okay, we'll see this occurring, which is where our frequency tends to go up and down. But the important thing is that as long as we are sampling at above the Nyquist rate, even though if we just join these dots together, we might see this sort of behavior occurring. As long as we have captured the frequency information, we can fully reconstruct that original signal. So we might have a reproduced signal that looks like this when we just join those lines up together. But we may reconstruct this signal. we can reconstruct the original signal using something called Fourier analysis. So who's heard of Fourier analysis before? One. Who's that sticking the hand up? So you guys, have you learned about the fast Fourier transform, FFT? We'll go through it in this class. I think it's a good and worthy thing that we'll go through it. And honestly, you'll use it far more than anything else that I could teach you. Okay, so we've got this stuff here. Let's summarize everything here, which is if we have an indication of likely frequencies of phenomena of interest, then we're going to sample at least the Nyquist rate. Okay, and when I say here an indication of the likely frequencies in a problem, you might not know exactly every frequency, but let's think about cases where you might know broadly what those frequencies are going to be. If you're looking at a vibration problem, for example, you're trying to measure the bending modes of a new vehicle chassis, you've probably got a good indication of what those frequencies are going to be from a CAD model. So they'll probably tell you what those natural frequencies might be. And if you know those are going to be in the order of, 20 hertz, then you would make sure you're sampling at least at 40 hertz. There's no point in sampling up in the megahertz for that sort of problem, because you're just collecting a lot of numbers that someone's got to do something with at the end of the day. Okay? So that gives us this idea of temporal resolution and introduces us to the idea of sampling rate and what impact it has upon our data. Let's see what happens if we sample below the Nyquist rate. So we sample below the Nyquist rate, then we can never reproduce those data properly. And this is not something that's particularly easy to teach through diagrams when you're as bad an artist as I am. So this is why lab 2 is going to be about doing this exercise using Python. So let's say that I need more than that. Let's say I've got some periodic signal here, and my first sample luckily happens to be on the very peak of here. My second sample is, let's say, 1.5 or 3/4 of a period later. So this would be below the Nyquist rate. 3/4 of a period later, I'd be here, then I'd be here, then I'd be here, 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 and here. So if I try and join these up now, that's awful. So my red signal might give me a good indication of the amplitude of this signal because it's got about the same amplitude because of the way that I've drawn this, but the frequency of this red signal is wholly different. So let's just say here, this would be the real period. The actual period of this signal would be, it would be this big one up here. So if we've got the reproduced period incorrect, then we haven't got the original frequency of this signal. So what we've done is when we sample below the Nyquist rate, we lose the frequency information of the signal that we've tried to sample. And there's a name for this, and the name you guys have probably heard before. This is called aliasing. Okay, it's called aliasing. Who's heard of that word before? You play video games? Yeah. You've probably heard of an anti-aliasing filter. That's probably where you've heard of it from. Okay, that's exactly what this means. And aliasing, we can think about what the word alias means. You probably know I like my English language. Alias just means to look like something else, okay, or a pseudonym. So if the reproduced signal looks like it has a different frequency, it has been aliased. There's also examples in this that you see in everyday life, or you used to see maybe in maybe a decade or so ago. If you ever watched sort of Formula One racing or maybe NASCAR on older televisions, sometimes it would look like the wheels of the cars are going backwards because they're being captured at a lower frame rate, or a low enough frame rate that it's capturing each wheel where it looks like it's slightly behind in each cycle. So that is aliasing, and it's another real life example. So we're going to investigate these two phenomena in laboratory 2. So what we're going to do is we're going to be reproducing the basics of what an analog to digital converter does. So we're going to take a signal, we're going to simulate a continuous signal. Now we can't really do that on a computer because a computer can only produce discrete sequences in time. So what we're going to do is we're going to produce a signal with a really big number of data points. And we're then going to look at the effect of what happens if we sample it at different sample rates. And we're going to see if we can see aliasing and see if we can see attenuation. Okay? Is everybody with me? Have we got any questions on this so far? Cool. Okay, so this is remember the two ways, okay? Aliasing and attenuation. If we're going to simulate what an ADC does, now aliasing and attenuation are consequences of the time resolution. These are consequences of discretizing. Discretizing, is that a word? I can't spell that now. It's very hard to do this with an audience sometimes. These are consequences of can't even say the word, of taking the time and taking discrete chunks of it. There are consequences of that, okay? So I said that an ADC does this not just for time, but also for value, okay? So if, for example, my signal looked like this, and I was recording, for example, voltage divided by volts. In the real world, voltage is a measure of potential difference in charge, okay? So for all intents and purposes, there are an infinite number of volts that we could record, okay? You get down into sort of chemistry and thinking about the number of charges you can have. There's not an infinite number, but for our purposes, the actual quantity has an infinite value resolution. So to record this as a number or as data on any form of digital electronics, so we're using an ADC, how do we store numbers on a computer? So as human beings, we have a base 10 number system. We have a base 10 number system, meaning that this is why it's really easy to multiply by 10. Okay, we like to think that we have a base 10 number system because we've got 10 digits. As Mohammed has said, we store numbers on a computer using binary. Okay, we store values in binary. Now, binary will just say is just a number, a finite number of switches. So an O is off, or 0 is off, and a 1 is on. Okay, I try and make the decision. Try not to think of them so much as 0 and 1. We'll think about them as off and on. Because if you think about them as 0 and 1, there's a tendency to think about them as numbers, and they're not. They're just 0 and 1. They are off and on. If you ever wondered why the TV power is that symbol, that's because that's an off and an on. Okay, so it's the on-off button has that symbol. And that blew my mind when there we go. At least one person is amazed by that. That's bloody amazing. Okay, if you learn nothing else from my course, that's a pretty cool fact. So what does this mean? This means that the number of switches that we have determines how many values we can store. The number of switches we have determines how many values we can store. So let's think about it. If we have, and in fact, the one thing I've not said, the number of switches is called the bit count. And what I'm going to go over in the following is a bit of a simplification of this process for engineers, because we just need to understand this stuff enough to use it. If there are any rogue computer scientists watching this, please don't correct me on any of the following, okay? Because I'm going to give a simple explanation for us simple engineers. So the bit counts, we give the symbol n. So let's do this. Let's say n. Let's do a simple example. So if n is equal to 1, then I can have my possible values. I can have a 0 or I can have a 1. Okay, with a 1 bit, I can store 2 values. So what does that mean? That means that if I've got a 1-bit ADC that's capable of taking anywhere from -10 to 10 volts, it means it can only separate them down into 2 bins. And it's going to say something is either anywhere from 0 to -10 or 0 to +10. Let's just write that down. What does this mean? Imagine we have a 1-bit ADC with an input of -10 to +10. So what it means is that for any value of voltage, it's only got 2 values it can store it as. Only 2 possible values that could be stored. So the 1-bit ADC could only record a voltage that is either below 0 or above 0. So this comes down, we introduced the concept of something called resolution. So resolution, which is the smallest change that an ADC can actually meaningfully separate. This is equal to the range divided by 2 to the power of n. So for this example, this would be 10 divided by 2, which would be 5 volts. Okay, so what this means for our purposes is that that's the gap between the individual vertical separation of each of our values that we can store. And it's doing this example for a 1-bit ADC was a little bit simplistic. So let's think about doing, if n is equal to 2, then I could have 2 zeros. I could have a 0 and a 1 and a 0, and a 1 and a 1. I've got 4 possible values. Okay, and that is simply 2 to the power of 2 is equal to 4. If n is equal to 3, well, we don't need to write them down. We could have 0, 0, 0, 0, 0, 1, 0, 1, 1, and so on. But we should know that 2 to the power of 3 gives us 8. So we have 8 possible values. And that means that if, for example, we had this exact same thing where we had a 10 plus or minus 10 volts, we would have 8 possible values. We would have, I did this wrong over here. Sorry, I just realized I've done this wrong. Did anyone pick up what I might have done wrong with this? I've set up here that has an input of -10 to +10. So the range of this is 20. Riley, good catch. Something about this number seemed wrong to me at the time, but I wanted to remain confident. So that should have been 20. Okay, so this is 10 volts. Okay, and this is then the size of each of those. Let's imagine this. So if I have a continuous signal that's going 10 volts to -10 volts, let's overlay on here. Let's say I can only tell if it's up here or if it's down here. Okay, that's what that means on there. And so each of these then has a 10 volts, which is where that number goes into. Okay, so we can see that a 1-bit ADC wouldn't be very good. This would give us 8 with a 3-bit ADC. I think that gives us 1.25. So 20 divided by, no, 2.5. Okay. So if we did this again with a 3-bit ADC, we would have a vertical separation. These would be effectively, these would be split into 4 each. So the ADCs that we tend to use in this laboratory are 16-bit ADCs. So we tend to use 16-bit ADCs in this lab. Now what this means for our purposes is if they have a plus or minus 10 volts, then our resolution is going to be 20 divided by 2 to the 16. It's a pretty small number. Okay, 0.31 millivolts. Okay, so that would be the smallest vertical separation between any of these values. Now, what this actually means for us is that when we have our signal, this is my original continuous signal, we've said that our sample rate tells us how far apart these samples are in time. Okay, now if our ADC has told us, or the ADC hasn't told us anything, if our ADC has a resolution such that I can only record at these discrete levels, then it actually means that this first one up here couldn't be recorded at this intermediate value. It would actually be here. This one would be aligned here, this one here would be here, and this one here would be here. So this signal, when I reproduce it, would be more like this. Okay, so we're jumping around. And what we're doing in here, we've no longer just got this discretization in time, we've also got this discretization in value. And what I'm going to do in this laboratory is give you a bit of code that does this bit for you, because this is actually quite difficult how to do this in Python, but it's useful to see the effect of changing bit count on this sort of resolution as well. So for your lab 2, okay, it's all going to be in the Jupyter Notebook. Now, video is going to be out on Wednesday night for this, and that's going to walk you through how to actually do this lab. Okay, how to take a signal, how to reproduce it, and how to simulate sampling data. Okay, and what you guys are going to need to be able to do is demonstrate aliasing and attenuation and then correctly chosen sample rates. But don't worry, I will tell you in the video exactly what those things that you've got to hand in for this are, okay? This laboratory is a bit more of a learning exercise. I'm not going to do a big hefty homework with this. I just want you to produce a small, maybe one-page report that shows a couple of graphs, aliasing, attenuation, correct sample rates, okay? And then I'm going to include the ADC bit count change in there as a bit of added bonus. Just I want you guys to learn from that. I'd like you guys to look at it and see how that works. Okay, I'm not going to test that part though. So are there any questions on anything that I've covered today? Anyone got anything cool to share with the group? Was the video any better today? I might have to work from home then. It's really astonishing because if I upload videos to YouTube, they upload in a heartbeat from university, and my connection here is okay. Okay, I'll probably try and keep working from home, but some of these videos I actually will have to be the lab videos I'll record in the lab. I'll maybe continue to do the lectures from home if my wife lets me get away with it. Well, guys, what I'm saying is actually, when you upload things from IIT, it's incredibly fast. So I don't know what's going on there. Okay, so guys, this lab video will be out probably around about Wednesday, but again, you've still got this lab's laboratory 1 homework is due in this coming weekend. And then very similarly, the lab 2, that will be due in the following weekend, okay? There's a really important sports game happening this weekend, I think. And of course, I hope you are all going to be watching the Calcutta Cup, which is the annual rugby game between England and Scotland. So the Rugby Six Nations is starting this weekend. And if you've never watched rugby, give it a chance. It's imagine like American football if it didn't keep stopping all the time and the game actually continued and they didn't wear those silly helmets and pads because they weren't scared to hit each other. You can watch it on NBC, I believe, or on the internet. But I used to play rugby and then everyone got a lot bigger than me. I see Ms. Murphy was supporting the Irish. I'll accept that. They're probably the only formidable team that are likely to beat England. Guys, I hope you all have a wonderful week, and I will see you all next week, whatever, in the video this week. Give me a message on Slack if there's any problems. I'll speak to you soon. Take care.